All right, welcome back, and let's look at the multiplication properties of exponents tonight. Remember that today in class we looked at how if I have a negative exponent, then really I'm not multiplying, I am dividing. So tonight we're going to look at what happens when I multiply the same base but different exponents. And I want to use this example here. Let's clarify some terms really fast. This 8 right here is my base, and this 2 is my exponent. All right, so now that I know that, this guy right here is my base. I'm raising my base to the second power, or I'm multiplying my base by itself. Now, remember that 8 times 8 is the same as 8 squared. It means I am multiplying 8 by itself twice. Now, the other thing to think about is this is the same as 8 to the first power, right? Because anything to the first power is itself. So what do you notice about when I multiply 8 to the first power by 8 to the first power? Well, I get 8 to the second power. Okay, let's look down here. Notice here I have 8 to the third power. Again, 8 is my base, and I'm multiplying it by itself 3 times because of my exponent. And this is the same as I could group these together and get an 8 squared, right? Because this is 8 to the first, 8 to the first, 8 to the first. And then I could think about having this guy separate. So this is like having 8 squared times 8 to the first. Well, if that's the case, what are you noticing here? Is this the same as 8 to the second power plus 8 to the first power? 8 to the second power times 8 to the first power? Notice that when I multiply 8 to the second power times 8 to the first, it is the same as adding their exponents. 2 plus 1 is 3. 8 to the third power is the same as 8 to the second times 8 to the first. Let's look at grouping this one down here. Let's say that I group these 3 together and I leave this guy separate for whatever reason. Wouldn't I get something like 8 to the third power? There's 3 of them, 1, 2, 3. And I'm multiplying, so I've got this 8 over here, and that's the same as 8 to this first power. What do you notice about this? This was 8 to the fourth. This is the same as 8 to the third plus 8 to the plus 1, or 8 to the fourth. So if I look at grouping this guy as 8 to the fourth, 4 8s together, or I could even look at grouping it as 3 of them together and 2 of them together. So this 8 to the fifth I could split up, and it could be 8 to the third times 8 to the second. And what do you notice about this? Again, I'm adding my exponents to get to this 5. It's the same as 3 plus 2. So this brings me down here to this concept of multiplying powers with the same base. Notice that all of my bases were the same. They were all 8s in every scenario. And that what I ended up doing was adding powers. So this says that for every non-zero number a, and integers m and n, that if I have a to the m, and I multiply by a, it's the same base, but this time to the nth power, that it's the same thing as a to the m plus n. This is the rule that I'm learning. Let's look at this guy. If I have 3 to the fifth, and I'm multiplying it by 3 to the fourth, what does this equal? Well, it equals 3 to the 5 plus 4, or 3 to the 9th. Notice it is not 3 to the 15th. When I multiply things with the same base, I have to add my exponents. You do this one. Let's say you have a variable, and your variable is h. and you have h to the second power, and you multiply this guy by h to the ninth power. What is my value of h? Hopefully you said it was h to the 2 plus 9, also known as h to the 11th power. All right, let's do some work with these. I'd like you to copy these 3 problems down on your own paper, and I'd like you to attempt them. Please pause me and see what you can do with these. All right, welcome back. Notice that your bases are the same in each of these, so all I have to do is add my exponents. Hopefully what you did was you recognize this is the same as 11 times 4 plus, or raised to the power 4 plus 3, or simply 11 to the 7th power. Down here, this one I had a couple more going on. I had 5 plus 2 minus 1, which is the same thing as 2 to the 7th power minus 1, or to the 6th power. Down here, I have 5 to the negative 2 plus 2. Well, this is 5 to the 0 power, because negative 2 plus 2 is 0. And anytime I have 5 to the 0 power, that is the same thing as 1, per our lesson today. Well done. All right, now I'd like you to try a few more. Write these problems, D, E, and F, down on your own paper. Please attempt these on your own, get your answer, and then unpause me and we'll check. Welcome back. Okay, let's try these. Hopefully you got 5 to the 9th. You recognize that when you add 4 plus a negative 3, you get a 1 for the letter E, and 2 to the first power is simply itself, it's 2. And then for F, you added all 3 up, and you got 7 to the 5th power. If you have any questions, look over these, please. And let's try something else. Let's look at multiplying situations where I have variables instead of numbers. So let's look at A, and let's make sure you have this written down. Let's say I have a situation where I've got x times x squared times x to the 4th. Notice, just like before I had numbers, this x is my base. My base is the same throughout. So what I need to do is I need to end up adding my exponents, just like before. So I take my base x, and now I need to look at my exponents. Remember that this is the same as x to the 1. So I have to take x to the 1 and add to it 2 and 4. And that is the same as x to the 7th. Anytime you have a variable out here without an exponent over it, it is the same thing as x to the first power, because any number to the first power is itself. Let's look at this guy down here. Let's say that I have 2n to the 5th times 3n to the 2nd. Well, here, you're going to end up needing to rearrange this a little bit. Notice that I have, I've got some constants out front that I'm going to end up needing to multiply. And then I have my base, and my base here is my n. So that's what I have in common. So let's use the rearranging property of multiplication. And let's say that I have my 2 times 3, and I'm going to pull those out, and then I'm going to multiply by my n. And here I've got n to the 5th times n to the negative 2nd. All I've done is rearrange. I pulled my multiplication out and put that right here. I'm still multiplying them, so nothing's changed, it's just simply the order. So these are my constants out in front, and I've got my variables in here in the other parentheses that I'm multiplying them by. Let's look at simplifying this. 2 times 3 is 6. And then in here, remember when I multiply by a base, it's simply the same as adding the exponents. So 6 times n to the 5th minus 2, which is the same as 6n to the 3rd. Your turn. I would like you to try these. All right, I'd like you to write these problems down, C, D, and E, on your own paper. I would like you to try them. Remember that your bases, if they're the same, you simply add their exponents. If you have numbers out in front, that you need to pull them out and multiply them separately, and then deal with your variables. Pause me, and let's see how you do. All right, welcome back. Hopefully on C, you recognize that there's this hidden 1 up here, and that you had to add that 1 to your 5 to get a to the 6th. Down here in D, hopefully you realize that you needed to pull out your 7 and separate that from your variables. And then once you had your variable and they were all the same base, you simply added them up. And again, you've got this other 1 that's going on right here. So you get n to the 6th. All right, down here, hopefully you remember to separate out your variables. And hopefully you got something that looked a little bit like this. And then hopefully you simplified and you realize this is the same as 18 times 2, or 36. And then you realize it's y to the 2nd plus the 3rd minus the 4th, which simply equals 36 y to the 5th minus the 4th, which is the same as 36y to the 1st, or simply 36y. This should be your answer right here. And I would like you now to look at a couple of other examples with me. Let's look at a situation like this. Notice in a situation like this, I have a base here where I've got C's and I've got another C over here, but this D is its own thing. When you have a situation like this, the first thing that we always want to do is we want to rearrange and rewrite, okay? So what we're going to do is we're going to rewrite our blues on one side and our yellows somewhere else. And remember that we're multiplying, so we need to keep that multiplication going on. So I'm going to keep my C to the 4th times C squared. I just simply pulled this guy here and I pulled this guy here. I'm just simply rearranging the order. And then I multiply by D to the negative 3rd. This is the exact same thing. It's just a different order. So now I can see, now that I've rearranged, the second thing I want to do is I want to simplify. So now it's really easy to see that this is the same as C to the 4 plus 2, and I'm multiplying this by D to the negative 3. And I can't do anything with it because they're totally different variables. I simplify this further and I get C6 times D to the negative 3rd. I don't technically need this multiplication in between because that's the same thing as simply writing these two variables side by side. So this should be what you end up with. But I can't finish yet. I have to simplify. Sometimes you have to simplify a couple of times. Remember that I don't want to leave stuff like this with a negative exponent, and a negative exponent is the same as division. So this is the same as C to the 6th over D to the 3rd. Remember that this is C to the 6th times 1 over D to the 3rd, and that this ends up being multiplied across, and that's how I got C to the 6th over D to the 3rd. Hopefully that helped explain. Let's look at another example like this. All right, this guy is just the same. It's just got some numbers in front. Don't wig out. Remember that in this situation, you're going to want to rearrange. Again, first step right here. So I'm going to rearrange. I like to do it by color coding. So the base that I have in common is my x. So I'm going to pull my x terms out. I also have some constants over here, so those are a little bit different too. And then I've got this weird y out here in the middle. So we are going to look at rearranging this. So I have my greens in one area, and I multiply that by my blues, and I multiply that by my yellows. Let's see what we get. Hopefully you notice that my 5, my 2, and my 3 are all of my greens. And I'm going to multiply those by my blues. I've got x times x to the 8th, and then I've got to multiply that by y to the 4th. All right, let's go up and check. I've got my 5, I've got my 2, I've got my 3, I've got my x's, and I've got my y's. Always go back and cross out. So you're going to rearrange, double check that you got all your terms by crossing out. And then you're going to simplify. And remember, when I simplify, my final answer should not have any exponents. So now that I've done this, let's look at simplifying this guy. Well, 5 times 2 times 3 is the same as 10 times 3, or 30. and I multiply that by x times 8. And that times y to the 4th. And x times 8 is x times 1 plus 8 times 30 times y to the 4th. This becomes 30 times x to the 9th times y to the 4th. Do I have any negative exponents? No. I'm good to go. This is my final answer. I would like you now to simplify A here, B here, and C here. Copy these down on your own and make sure you're going through the 3 steps that we talked about. Rearrange, double check by crossing out your terms that you've used, and then simplify. When you simplify, your final answer should not have any negative exponents. What if you're told to use scientific notation? The cool thing is you can apply the same concept to solving scientific notation questions. Let's say you're told to simplify this problem. 7 times 10 squared, the quantity, times the quantity 4 times 10 to the 5th. Well, let's look at this. Which one of these terms is my base? My 7? No, I don't have another 7. My 10? Well, yes, I have a base. These are both the same number raised to an exponent. So my 10s are a base. So let's highlight those so I can easily identify that these can get grouped together. Now, notice all I'm doing is multiplying. So I can rearrange these, and it's going to look like this. Let's make sure. I'm going to color my 7 and my 4 because these are constants. They don't have any other number attached. As a side note, remember that if I was multiplying 2 times 8 times 3, it doesn't matter if it's 2 times 3 times 8, or if it's 8 times 3 times 2, or 8 times 2 times 3. All of these are going to end up giving me the same number. When you're multiplying, you can move things around. The order doesn't matter. So let's think of moving these around where I get my constants over here, 7 times 4. All right, I've got these terms. Always cross out the terms that you're using. And then I've got this 10 squared times 10 to the 5th. All I did was rearrange my 7 and my 4 and my 10 and my 5. I'm sorry, my 10s. So 7 times 4 is the same as 28. And let's look over here. Remember that 10 times 2 times 10 to the second power times 10 to the 5th power is simply the same as 10 to the 2nd plus 5. Or in this case, 28 times 10 to the 7th. Well, we're not done yet, because remember when we write in scientific notation, my answer has to be greater than 1. It can be equal to 1, but it has to be less than or equal to 10. It's got to be in this range. 28 is greater than 10. I can't have that happen. So I'm going to end up needing to make 28 smaller by moving in a decimal. So this becomes 2.8 times 10. Uh-oh, I had to move a decimal in. Which way did I move my decimal? Well, I moved it to the left, so technically my number should be bigger. So I need to add another 10. In order to get back to 28, I have to add 10. 2.8 times 10 is going to give me 28. So because I went smaller, I had to add another 10 up here. I've got this 10 I've got to multiply by to get back. So now I'm back to 2.8 times 10 to the 1st plus 7th, or 2.8 times 10 to the 8th. This is my final answer. Just to review, if you're going to move a decimal point in over here, then you're going to have to add another 10 that you multiply by. Now, conversely, let's look at a different situation. Again, I want to pull out my numbers that aren't my base, and I want to identify the numbers that are my base that I can add the powers, and I want to rearrange as my first step. So when I'm solving this, you're always going to rearrange first. And we're going to put our constants out here. And we're going to put our bases in here. And you're going to get something like, hopefully you've already got this before me. 9 times 7, cross out my terms. And then I've got this 10 to the negative 6 times 10 to the negative 9th. 9 times 7 is 63. And I'm going to multiply that by 10 to the negative 6 plus the negative 9th. Well, 10 to the negative 6 plus the negative 9th is 10 to the negative 15th. But we're not done. I want to write it in scientific notation, and scientific notation has to be between 10 and 1. I've got 63. That's not in between 10 and 1. So I'm going to end up needing to move this guy in again, and based on what I saw last time, when I move a 10 in to make my number smaller, I end up having to multiply by an additional 10. Okay, well, now I've got this 10 to the 1 and 10 to the negative 15. Or, in other terms, 6.3 times 10 to the 1 plus the negative 15, which is the same as 6.3 times 10 to the negative 14th, because 1 plus a negative 15 is a negative 14. At this point, it satisfies the need to be between 1 and 10, and I've got scientific notation over here. You see how helpful this is? On your own now, I would like you to simplify A and B and make sure that your final answer is in scientific notation, where your answer is in between 1 and 10, times 10 to some power. If you get stuck, rewind the video a little bit and watch the part on scientific notation. Please have your work ready and be able to show me your steps tomorrow for class. Let's look at a real-world application. Let's look at this scenario where you're given this fact. A human body contains about 3.2 times 10 to the 4th microliters of blood for each is a key word, each pound of body weight. Each microliter of blood, back up here, contains about 5 times 10 to the 6th red blood cells. And I want to find the approximate number of red blood cells in the body of a 125-pound person. Okay, I've got some things going on. Let's come back up. I've got microliters, I've got pounds, and I've got red blood cells. What is the relationship between these? Well, let's write down what I know. I know 3.2 times 10 to the 4th microliters. And I know that that is per pound. Right up here. Each pound has that many microliters of blood. Each microliter of blood contains about 5 times 10 to the 6th red blood cells. All right, so I know 5 times 10 to the 6th red blood cells equals what? Well, let's go back. Each microliter of blood contains. Oh, this is the same as equals. So that's each microliter. In this case, 1 microliter. Okay, and I want to know how many red blood cells are in the body of a 125-pound person. All right, so we're going to start with our 125-pound person. So I know that I have 125 pounds. I'm going to multiply that by something. Remember your ratios that we did? Let's come up here and let's look at expressing this guy in a ratio. This is the same as 3.2 times 10 to the 4th microliters per 1 pound. And down here, I can express this 5 times 10 to the 6th red blood cells per microliter. So if I'm starting with a 125-pound person and I want to get to red blood cells, what do I know that'll cross out pounds? Well, let's look up here. I know pounds. 1 pound is 3.2 times 10 to the 4th microliters. And that's per 1 pound. So my pounds cross out and now I've got microliters, but I want to get to red blood cells, right? I want to look at the number of red blood cells. So to get there, I'm going to have to cross out my microliters. So how do I do that? Well, I'm going to have to divide by microliters. So I know that this relationship up here will give me microliters to blood cells. I'm going to cross these out. And what do I know about the relationship between microliters and blood cells? 1 microliter is 5 times 10 to the 6th blood cells. Okay, now I'm left with some pretty icky math, but my pounds crossed out, my microliters crossed out, and I'm left with blood cells. Is that what it wants? Why, yes it is. So let's do the math. I've got 125, and I'm multiplying that by 3.2, and I'm multiplying that by 10 to the 4th, and I'm multiplying that by 5 times 10 to the 6th. All right, this doesn't look that different than what we've been doing. So what we're going to end up having to do here is rearrange. I have constants. I've got them here and here and here. And I have 2 bases that are raised to powers. So let's look at rearranging. I've got my green, and I've got my bases, and I'm going to end up multiplying and rearranging. So 125 times 3.2 times 5. I've got this term, and this term. And I'm multiplying that by 10 to the 4th times 10 to the 6th. Well, in order to figure out what all of this green goo is over here, I'm going to need a calculator. Fortunately, my calculator tells me it's a nice even 2,000. And this 2,000 is times 10 to the 4th times 10 to the 6th. Remember my rule when I multiply the same base with exponents? It's the same as adding their powers. In this case, I get 2,000 times 10 to the 10th. Cool. Well, one problem with that. If I'm given scientific notation up here, I've got to put it back into scientific notation. If that's what your dimensions are starting in, that's what you need to get it back to. So in order to get it back to scientific notation, I need to get this 2,000 down to just a 2. How do I do that? Well, I got to bring a decimal in 1, 2, 3 places. So I get 2.0. And that's going to add a 10, right? How many spaces did I have to bring this guy in? 3. So to get back to my 2,000, I've got to multiply 2.0 times 10 to the 3rd. And then I multiply that by 10 to the 10th. And so what I end up with as my final answer is 2.0 times 10 to the 13 because I add my powers. And this is the approximate number of red blood cells in, I'm sorry, not microliters, blood cells in a 125-pound person. Okay, I would like you now to consider how many red blood cells would be in a 160-pound soccer player. So if you have a 160-pound soccer player, how many red blood cells does he have? Go back through this process. See what you can do, and have your answer ready for me tomorrow in class.